This week in lab we are doing recrystallization and melting points. Recrystallization is another purification technique. We've done several purification techniques so far this semester, but it's another way to purify compounds. It's a way to purify solids. It must be a solid to recrystallize. We cannot get crystals if it's not a solid. There are four important concepts to consider when we are recrystallizing. One is the solubility of our compound. Another important concept is saturation level. Next is exclusion. And finally, nucleation. Now I'm going to discuss each of these separately. So let's first talk about, we'll just go in order here. Let's talk about the solubility. The choice of solvent is very important. The most important concept of solvent choice is that I'm going to put a star beside this one. This is the most important. It must dissolve the solute at high temperatures, but not at low temperatures. We want everything dissolved at the high temperature, so say at boiling, we'll heat it up to boiling. And then as we cool down, we want the compound to fall out of solution, to crystallize out at the lower temperatures. So we don't want it soluble at the low temperatures. Now, if we can't find one solvent that meets this criteria, dissolving it well at high temperatures but not at low temperatures, then we can use a solvent mixture. We don't have to use a single solvent. We can use a solvent mixture. In fact, this week in lab, we are using a solvent mixture. I don't remember the solvents that we are using, but we are using a mixture. We are using water and ethanol. So we are recrystallizing benzoic acid, and benzoic acid is not very soluble in water, but it's extremely soluble in ethanol. It's too soluble. It will not come back out at the lower temperatures. It's soluble at all temperatures in ethanol. Well, in water, it's not very soluble at all in anything. So we use a solvent mixture, and we can get just the right solvent then to dissolve it well at high temperatures and not at low temperatures. So if you can't find a single solvent, we use a solvent mixture. Second, I'll put this one as first criteria here for solvent choice. Second one, that one is the most important one. Second one, this is also very important. I'll put a star beside this one too. The solvent must not react with the solute. We don't want to choose a solvent that would react with our compound, because then it's going to make something else and we no longer have our compound anymore. So we need a solvent that will not react with the solute. Now the last one that I'm going to put up is nice to have, but this is not an absolute requirement. You must have the first two. That's why I've got stars beside those. The third one here that I'm going to put up is just a bonus. It's nice to have this, but it's not an actual requirement. It's best if the solvent is non-flammable. Now that's just nice, then we don't have to worry about a fire when we're recrystallizing. So it's nice if it would be non-flammable, but it's not an absolute requirement. We can use flammable solvents, we just have to be a little bit more careful. It's nice also if it is non-toxic. Now again, that's not a requirement, but it's much nicer to have something that's non-toxic. Otherwise, we will have to take special precautions. We'll have to do use the solvent in the hood, and maybe put some gloves on or something. Use a little bit extra safety precautions, but you can still use a toxic solvent. It's just better if it's non-toxic. Then you got less to worry about. It's nice if it's inexpensive. We would like something that's cheap. Not a requirement, but certainly is nice. We don't like to have to spend a lot of money on solvents, so it would be nice if it's cheap. And lastly, again, not a requirement, but just nice to have, if it is volatile. And that's so that it can be removed from the crystals once we collect the crystals. Makes the drying of the crystals a lot easier. So, those are some criteria to consider when we choose a solvent. First two are absolute requirements. It must dissolve the solute well at high temperatures, not at low temperatures. And we must have a solvent that will not react with the solid. Last one is just nice to have, but not a requirement. Let's talk about the saturation level. We've already done solubility, so let's talk about saturation level. We want to, when we are recrystallizing, it's important to use a minimal amount of solvent. If you look in your procedure, it will say, I'm certain it will say, I haven't looked at it for a while, use a minimal amount of solvent. And everyone always asks me, well, how much is that? I don't know. Smallest amount that will dissolve your compound at boiling. That's the minimal amount. This is, you want it to dissolve the solute at boiling. So the smallest amount that you can get away with amount that you can get away with to dissolve the solute at boiling. Now, if we've used the smallest amount of solvent, got it just dissolved at boiling, no extra solvent, then we have a saturated solution. This would be a saturated solution there at the boiling. It's dissolved all it can hold and no more. We've got no extra solvent, so it's a saturated solution. saturated solution at boiling. Now, as we cool the solution, as we allow it to cool, remember we chose a solvent that would dissolve the solute well at the high temperature at boiling, and we chose the solvent one that would not dissolve it well at low temperatures. So as we cool, then the solution becomes supersaturated. That means that it has more than it can dissolve. The solvent has more solute than it can hang on to. And so crystals start to come out of solution. The solvent can't hang on, can't dissolve that much. And so it comes out of solution. So we have the saturated solution becoming supersaturated and crystals come out. Okay, so saturation is important. We need a saturated solution at boiling, and then when we cool it becomes supersaturated and we get crystals to come out of solution. Let's talk about exclusion. Say we have a beaker here, and we have our solvent. And we have the solute dissolved in the solvent. Say those are the little squares. And we've got a small amount of impurity. The little stars are the impurity that's in there. The squares is our desired compound, our solute, and the little stars there are impurities. Now, we said we had a saturated solution at boiling, and then as you cool it becomes supersaturated, and so we have to have the material come out of solution. The solution cannot hang on, the solvent cannot hang on to that much material at the lower temperatures. So it starts to crystallize. We get little crystals starting to grow here on the bottom or maybe on the sides. And then another square will come in here. So whichever compound there is a majority of, and there's a majority of the squares there, that's the one that's going to come out first. The impurities will stay in solution. They stay dissolved. Now, if a star happened to have come in here and try to fit in, you can see it doesn't fit right. When things crystallize, they like to pack as tightly as possible. They don't like a lot of extra empty space. And the little star does not fit in there. So even though it may try to come on, it'll come right back off. Any of these can come back off. They'll fit onto the crystal and they'll come back off into solution. So the star comes in here and tries to fit and it doesn't work. It doesn't fit right. So they'll go back up in here into solution, and now maybe a square will come in there and fit, and then maybe another square. And so that's the exclusion. It excludes the impurities because they're not going to fit right. And so this is how we are getting more pure. Each time you recrystallize, you get more pure and more pure. Now we may have some where a square accidentally gets in there, or a star, accidentally gets in there. So it may not be 100% pure, but it's better than what we started with. So each time we recrystallize, it will get more pure and more pure and more pure. Let's say we started off and it was 80% one compound and 20% impurity. After we recrystallize, it gets we get more of whichever one is the majority of. And so now maybe it's after the recrystallization, maybe it's a 90-10 mixture. 90% we'll say squares and 10% stars. We recrystallize a second time, and now maybe it's 95% squares and 5% stars. Recrystallize a third time, now maybe it's 99% squares. Fourth time, now maybe it's 100%. So each time you recrystallize, it gets more pure and more pure. Now for recrystallization to work, you've got to have one compound that's in excess of the other. There's got to be more of one than there is the other. If it's a 50-50 mixture, if I had half squares and half stars, we would get half and half coming out. You have to have one in an excess of the other. You got to have more of one than the other for recrystallization to work. A 50-50 mixture will not work. Okay, so that's exclusion. We exclude the impurities as we recrystallize. Now, it is important to when we go to recrystallize, to let it cool slowly. We want it to cool nice and slow, so that these will have time to come on and off, on and off. If a star comes in here and tries to fit, it has time to come off if you let it cool slowly. If you cool it quickly, then instead of a crystallization, it just precipitates. It just falls out. It's a precipitation rather than a crystallization. Crystals, you know what a crystal looks like. It's nice and shiny, and you know what a crystalline material is. They're usually got a real shiny surface and everything's fit in there. Precipitant is just like a powder. Precipitant is, we just get a powder out. So if it cools too quickly, you get precipitation. Cool it nice and slow, and that gives the crystals time to grow. Okay, let's talk about nucleation. Nucleation is something for the crystals to grow on. Maybe it's just a little speck of dust in there. You can't even see it. That's something for the crystals to start growing off of. Something for them to stick to and get to growing. So maybe it's just a speck of dust. It could be scratches on the inside of your reaction tube or a beaker, whatever we happen to be using. You're using, I think you're using a reaction tube in your procedure. I think that's what it says. So just a scratch on the sides of the glass. That little scratch on the, I can't draw a scratch on there. There's not enough. Maybe it's a scratch on the side. And that gives us a place for the crystals to start growing, to stick to, and start growing off of. So, anytime you're recrystallizing, pick out the oldest, most scratched up reaction tube that you have in your kit, and you will get the best results. If you get a brand new reaction tube, there's no scratches on it, there's nowhere for the crystals to start growing. So oftentimes it's difficult for the crystals to get started. So like I said, pick out the oldest, most scratched up reaction tube you have in your kit, and you'll get your best results. You can also use a seed crystal. So like, so we had the speck of dust, scratches. You can use a seed crystal. What is a seed crystal? You may not have a seed crystal. Seed crystal is if we have some, maybe from a previous experiment or something, or maybe we bought some of some pure benzoic acid, is what we're recrystallizing this week. So if we had a little small crystal of pure benzoic acid, we could put that in there. That's the seed crystal. So we put a crystal in there, and then that gives us something to start growing off of. Then it can grow that one bigger. That's a seed crystal. You start with a small crystal, put it in there, that gives something to grow on and just gets it bigger. Okay, so that's nucleation. Just something for the crystals to grow on. Okay, so that's the recrystallization part of the lab. We're going to talk about melting point now. Melting point is really not a good term to describe what we're doing. It's really a melting range. Rarely will a compound melt at an exact point, one exact temperature. So rarely is it a melting point. It's normally a melting range. It will start melting at a certain temperature, and then it will finish melting at another temperature. That's the range. So maybe, I don't know, benzoic acid this week, I think it's 120 something. So maybe it starts at 118 degrees, and when we start to see some liquid, so melting, going from a solid to a liquid, 118 maybe to 120, something like that. That's a range. When it starts to melt, when it's finished melting. When we just start to see some liquid, and when it's all liquid, no more solid present. So it's really better to say melting range rather than a melting point. So in your lab this week, I want you to report a melting range, and in all labs in the future, report a melting range when you first start to see some liquid and when it's all liquid. Now, this range will tell us something. Impurities in the crystal will lower our melting range and will also broaden the range. So let's say in our benzoic acid, let's say we had some impurities in there, and instead of maybe melting up here around 120, it melts maybe 105 to 115. So you can see, so this would be the impure. The impurity lowers the melting range. You can see it's lower numbers. And it broadens that range. See, now there's a 10 degree difference. Up here there was a 2 degree difference. To be pure, compounds should melt within a 1 to 2 degree range. When you see a 10 degree range, you know it's impure. Pure compounds should melt in a 1 to 2 degree range. Now, to measure melting points, we have melting point apparatuses in the lab. You are going to use a melting point capillary tube. Hopefully you can see this. It's just a little tiny tube. One end of the tube is open, one end is closed. So to take the melting point, you got to get your sample inside of the capillary tube. So take the open end. I didn't bring any compound in here, but let's say there's some compound on this paper. Just take the open end and press it into the compound, into your sample that's there. Take the open end, press it in. Just get a little bit in the tip. Just need a little bit in that open end. Long as you can see it, that's enough. Don't fill the tube up. You just need a little bit, a little small amount. The melting point apparatus has a magnifying glass on it, so you'll be able to see it plenty well. Now, we need to get it from the open end. We got a little bit there in the open end of the tube. We need to get it down into the closed end. So we need to tap it down. Now, you can tap it on the bench with your hand, but it'll take forever. We have a very sophisticated piece of equipment that will tap it down for us. We just take a big large tube. I said sophisticated, nothing sophisticated. Just a glass tube. Take the capillary tube, closed end, pointing down, and drop it in. And it will bounce. It just bounces and bounces and taps it down for you. Now you may have to drop it 2 or 3 times, but it will tap it down to that closed end. Now, once you got it in the closed end, then you can put it in the melting point apparatus and measure your melting range. So it's just a glass tube. Now it happens to have a pencil taped to it. Don't take my pencil off, please. I put that on there for a reason, because these glass tubes tend to roll off into the floor and break. So I taped a pencil to it to keep it from rolling. So that way we don't break so many tubes. Now with your melting point apparatus, we want to heat those slowly. We don't want to heat them too fast. If you heat the melting point apparatus too fast, so if you take and crank it up on high, what happens is inside there's I can't draw very straight here. There is a heating block. And your capillary tube goes into that heating block. There's an opening there. You will see it when you get in there. So the capillary tube goes down into the heating block. And then here on the other side there is a thermometer. And this goes out to a digital readout. Now, if we heat too fast, the heating block heats up very quickly, but it takes time to transfer that heat. The heat's not transferred instantaneously, so it takes time to transfer it into your sample. So that's a little bit of a delay. It also takes time for your thermometer to read that temperature, for this to transmit the reading back to our digital readout. All of that takes a little bit of time. So if we heat too fast, the block is continuing heating, and this is taking its time. It's much slower about reading, and it's much slower about transferring it into your sample. And so what happens is that the melting range that you see would be lower than it really is. it hasn't had time to catch up to the heating block. The heating block is maybe, 100, and this is still reading, 95. It's not caught up to the heating block if you heat too fast. If you go nice and slow, there's no problem. Go nice and slow, this will be 95, this will read 95. But if you go too fast, that heating block is heating faster than the thermometer can keep up. So that makes your melting range lower. Now, you want to heat. There's some, so you want to heat at the proper rate. Well, how do you figure that out? In there, by the melting point apparatuses, there's some temperature curves. On the y-axis is temperature, and on the x-axis is time, minutes. And there's all these curves. Here is a setting of 2, and here is a setting of 4. Maybe here's a setting of 6. And maybe 8, something like that. So you're looking I don't remember, like I said, I don't remember exactly what benzoic acid melts at. It's 120, 121, 122, 123, somewhere along in there. I know it's about 120 something. So what you're looking for, a good rate, you want something in between about 10 to 15 minutes. That's what you're looking for. Might could go up to 20, but you're really looking for about 10 to 15. So just extrapolate back. Here's 120, and we want about 15 minutes, so that looks like about a setting of 4, maybe a little bit less than 4. Now that's just my drawing. Look at the real chart. I'm just making this up out of my head. So look at the real chart and see what kind of a setting, which of the settings you would need to set it on. See, we don't want a setting of 8. Setting of 8, probably get it there in 2 minutes. That's way too fast. You're looking for about 10 to 15. Somewhere along in there. Any shorter than that, that's too fast. Any longer than that, you're just here all day. It's nice if you want to wait 30 minutes. That would be fine, but it's just going to take forever. So a good compromise is 10 to 15 minutes. It'll get you a pretty good number. So melting points can be used to tell us something about the purity of our compound. So again, impurities will lower the range and broaden the range. It can also be used to help confirm the identity of a compound. So let's say we have some unknown. We can go take the melting point of this unknown and then compare it to a known compound, so you can use it to help identify. Now the best way, if you want to identify a compound, if you happen to have some, let's say we've got some unknown, a bottle here that maybe somebody didn't label, and it melts at 100 degrees. Well, I've got another bottle here of something that is known, and we took a melting point of it, and also melts at 100 degrees. Can we say those are the same thing? No. There's lots of compounds that melt at 100. But one thing we can do to help confirm that they are the same is to take and mix those two. Mix them, and then take a melting point of that mixture. If they're not the same, if they are different compounds, what will happen? Well, one will be an impurity in the other. So that would lower the melting point and broaden the range. So if they're different compounds and you mix them, it acts as an impurity, so we can tell they are different. If they are the same compound and you mix them and take a melting point, then it should still melt at 100 degrees, if that's what the original compounds melted at. So you can use that to confirm a compound, the identity of a compound. Just mix them and retake the melting point. If they're the same, you will get the same melting point. If they're different, you're going to get a lower and broader melting point. Okay, so let's now talk about the melting points, how structure affects melting points. We did this with boiling points, how structure affected boiling points before, and let's look at it with melting points. Let's look at how structure affects the melting point. Really should say range, but I'll stick with what most of the textbooks and stuff are going to say, melting points, but really it should be a melting range. One of the biggest structural effects, or the biggest structural effect, it is the biggest structural effect, is ionic attractive forces, ionic bonds. Things with an ionic bond will have a very, very, very high melting point. Let's look at an example. These will have our highest melting points. These ionic bonds. In other words, salts. Here is an alcohol. This one has a melting point of 41 degrees. We know that can be an acid, so let's take and react with some good strong base. Sodium hydroxide, that's plenty strong enough to pull off the hydrogen. And then that gives us an ionic bond. So the OH grabbed the hydrogen, we made water. But we have an ionic bond here. In other words, this is a salt. And these will have the highest melting points. The melting point of this one is 382 degrees. You can see very, very high. Many salts are so high we can't measure them. So oftentimes we can't even get to a high enough temperature to get them to melt. So that's one big structural effect on melting points. Your ionic bonds will have the highest melting points. Can you think of another good strong interaction that might affect melting points? Hydrogen bonding. This is our next biggest structural effect. If the compound has hydrogen bonding, has the capability of hydrogen bonding, then that will have a much higher melting point than something that can't hydrogen bond. Let's look at some examples. Hey, I've got benzoic acid here. I was wondering what the melting point was. I see I was pretty close. Melting point of benzoic acid, 121 to 123. This carboxylic acid has got very strong hydrogen bonding. Let's compare that to an alcohol. So we just had this one up there just a moment ago. We said that one was 41 degrees was the melting point. You can see how much carboxylic acids have much stronger hydrogen bonding than alcohol, but alcohol is still hydrogen bond. Carboxylic acid is just stronger hydrogen bonding because we can get, these will dimerize, we get twice the hydrogen bonding. So you can see how much of a difference that makes. Let's look at one here about the same size that can't hydrogen bond. Let's look at that one. Got a methyl group out there, so no hydrogen bonding here. And let's look at the melting point. Minus 93 degrees Celsius is the melting point. So you can see the effects of hydrogen bonding. No hydrogen bonding. All these are about the same size. A little bit of difference, but pretty close. No hydrogen bonding. Some hydrogen does have hydrogen bonding. And then very, very strong hydrogen bonding with the carboxylic acid. So hydrogen bonding is a big effect on the melting point. It will raise those melting points. Size matters with melting points, just like it did with boiling points. Let's look at methane. Melting point of methane is minus 182. Let's go bigger. Butane. Melting point is minus 138 degrees Celsius. So you can see a larger molecule has a higher melting point. Here's hexane, 6 carbons. Melting point, minus 95. So we've got an even higher melting point. Bigger molecule, higher melting point. Now, just like we saw with the boiling points, so the bigger we get, higher the melting point. Just like we saw with the boiling points, higher the boiling point. Also with the boiling points, we talked about how being in a ring had a higher boiling point. Same thing with the melting point. Being in a ring, you have a higher melting point. So let's, instead of hexane, let's look at cyclohexane. So cyclic molecules have a higher melting point. Cyclohexane melting point is 4 to 7 degrees Celsius. So you can see it's higher than the hexane. And then if we had, let's do one more example. If you got something that, a cyclic that could hydrogen bond, put an alcohol out there, we get even higher. Melting point of this one's 20 to 22 degrees Celsius. So just like we talked about here a moment ago, hydrogen bonding will raise the melting point, give you a higher melting point. So size matters, having an ring matters, hydrogen bonding matters, or an ionic gets even higher. So far, everything that I've talked about here is exactly the same as what we talked about when we did boiling points. There is a difference. All these things mattered on both boiling points and melting points. Size matters, ring matters, all that matters. This is the difference. With melting points, symmetry matters. When we did boiling points, it was about having a chain versus branching. Branching lowered the boiling point. Here we're looking for symmetry. Molecules that are symmetrical generally have higher melting points. If there's any kind of symmetry. Let's look at an example. Let's compare two molecules. Here's two alcohols, exact same size. They both have 4 carbons, same number of hydrogens, and they both have the 1 oxygen. They're both an alcohol, exact same size. So it's nothing to do with size. But one of them has symmetry. This one is symmetrical. You can see there is symmetry through here. The bottom is just a mirror image of the top. That symmetry within the molecule gives us a higher melting point. This alcohol here, melting point is 25 degrees Celsius. The other alcohol, melting point is minus 90 degrees Celsius. So that symmetry raises a melting point. Any molecule that is symmetrical will have a higher melting point. And that makes sense if you think about it. These symmetrical molecules can pack into the crystal tighter. And they pack in there, fit in there better because they're symmetrical. They pack in tighter, there's less open spaces, and so they will stick together tighter. Makes it harder to melt it. Let's say we got go back to my squares. Let's say that molecule is like a square. That's something that's symmetrical. You got very little space in between the molecules, then the crystal is packed in very tight. That's going to have a high melting point. If a molecule is not symmetrical, I don't know, just draw something weird. You can see they can't pack in tight. There's all these, if they're weirdly shaped, if there's no symmetry, then you got all of these spaces in here that's just empty, just air. So that makes it easier to break it apart. Remember, to melt, you have to have the molecule come off of the solid. It comes off and flows as a liquid. That's melting. Flows as a liquid. And if you've got nothing around it here really holding it down, it's easier for it to melt. So these that are not symmetrical have lower melting points. The ones that are symmetrical will have a higher melting point because they pack in tighter in the crystal. Okay, so that's how structure affects melting point. Most of it's very similar to the boiling points that we talked about before. But this is the part that's different. It's symmetry here with the melting points. Symmetry does matter. Didn't matter so much with the boiling points. There is about being whether you had branching or not. So a little bit of difference. So you can expect a question on your lab midterm. That's coming up in I think it's 2 weeks, I think. Where I'll list several molecules out and say put them in order of their increasing melting point. So you don't have to know the numbers, you just have to be able to put them in order. So use this structure, these structural effects to be able to put them in order. I'll do the same thing with boiling point. So you'll have one with melting point and one with boiling point. Okay, now let's take a look at our procedure here. So much of this I've already talked about. We are dissolving the compound in a minimal amount of solvent at boiling. And then after we let it cool, and we want to cool slowly, so the best way to cool slowly is to take, give me a paper towel. Take some paper towel. Take your reaction tube, we'll say this is your reaction tube that you've just recrystallized. So you got it up to boiling. So as soon as it gets to boiling and it's all dissolved, no more solid in there, take it off. You can let it sit there and boil forever. It's not going to, no more is going to dissolve. If it's not dissolved at boiling, add a little bit more solvent. Get it back to boiling. Still not all dissolved, add another couple drops of solvent. Get it back to boiling. You keep going until it's just dissolved and then stop. Take it off the heat. Take the paper towel, wrap it around your reaction tube, and you can set that in a beaker. And just let it sit there and cool slowly. Don't touch it. You want to leave it undisturbed to cool slowly. And then you'll get the best crystals out that way. If you keep checking on it every now and then, you're shaking it essentially as you're pulling it in and out. You're shaking it, disturbing it, then you wind up with little tiny crystals, or it may just precipitate. So you want to go nice and slow, so put a paper towel around it. Okay, so after it has had time to cool to room temperature, we'll take and filter it. You'll filter it with your Hirsch funnel, and then you're collecting the solid on the Hirsch funnel. Notice the color of the crystals. The original contaminated benzoic acid that we're starting with, you'll see it's got a pretty tan color to it. A little brown or tan color to it. Benzoic acid is supposed to be white, supposed to be colorless. As you recrystallize, it should improve. It should get, less color to it, starting to become more white. So note that color in your notebook as you recrystallize. So you've collected your sample on the Hirsch funnel. Scrape that off on a weight paper. Save. Let that set back and dry. But we don't need to dry all of it because we're going to recrystallize a second time. So save just a little bit. Put a little bit on a piece of weight paper, and then you're going to take and recrystallize the rest of it. So save a small amount. You just need enough for a melting point. You don't need a large amount. We're going to recrystallize the rest of it. We're going to do a second recrystallization, and this should make it even more pure. So go through the exact same thing again. Put it in your reaction tube. Slowly start adding solvent. Get it up to boiling. Still not dissolved. Add a few more drops. Get it back to boiling. Still not dissolved. Add a few more drops. Keep going until everything's dissolved. Take it off. Let it cool slowly. Collect the crystals on a Hirsch funnel. Now, we need to get a melting point of the samples. The problem is we're recrystallizing with water and ethanol. Water takes a long time to dry. And any of the solvent that's still on the crystals will act as an impurity. So that would lower a melting point. They really need at least a day or two to dry fully, to be completely dry. So what we're going to do is we're going to save those samples. You're saving the 2 recrystallizations. Remember, don't forget to save a little bit off that first one. And then we got all of the second one. You can save those till next week, and we will get a melting point on those next week. That will give them a full week to dry. And the melting point doesn't take long. I know we have another lab next week. We have sublimation. Sublimation is a quick lab. And then all you'll have is just the melting point to take from this week's lab. So this week, though, I do want you to do a couple melting points so that we have something to compare with. I want you to do a melting point on pure benzoic acid. And we have some pure benzoic acid already sitting out. I want you to take a melting point of the contaminated benzoic acid. We'll just put BA for benzoic acid. So these I want you to do this week. Do melting point this week. Now next week, I want you to do the melting point of your first recrystallization and a melting point of your second recrystallization. So you will save those samples for next week. Put them in a drawer that's underneath your station. Label the drawer. Take some of that blue painter's tape and label it with your name on there so that nobody will bother it. So if you're in one of the later labs in the week, don't touch them if they've got somebody's name on them. Choose a drawer that doesn't have a name. There's plenty of drawers there underneath your station. So you're doing 2 melting points this week, and you're recrystallizing the contaminated, and you'll do melting points on those 2 recrystallizations next week. So what we're getting out of this, we know where we started. The contaminated is what we started with. We know where we need to go. We need to get to the pure. And you've got your first recrystallization and second recrystallization. Were the 2 recrystallizations enough to go from the contaminated all the way to the pure? Might be, might not. Discuss that in your conclusions. Talk about if 2 was good enough. Maybe we should have done 3. We're only going to do 2, but just talk about it. You've got the numbers there to compare with. So if this one matches the pure one, then 2 was enough. If they don't match, then we probably should have done more. So discuss that in your conclusions.